Science shouldn't feel like a closed door. Welcome to Human Verified, your backstage pass to the world of high-stakes research and the business of staying alive. My name is Gina Winchester, a Native American scientist, professor, author, and I've created this space where we swap dense academic jargon for fresh, no-nonsense insights. Whether I'm deconstructing pharmaceutical breakthroughs, clinical trials, or the how this is legal side of STEM business, I'm here to bridge the gap between the lab bench and your daily life. It's rigorous research met with real-world storytelling because understanding how science works is the ultimate power move. Resistance really is futile. There is a lot of anxiety in the world today about machines replacing us or algorithms taking over our lives. I've argued that no line of code or silicon model can truly replicate the biological masterpiece that is the human body. AI can certainly assist us, but it doesn't live. While we have to be thoughtful about the intentions of the people behind the machines, the technology itself isn't the risk. It's the potential solution. The application of AI that keeps me up at night, in the best way possible, is bionics. For a century, movies have teased us with superhumans and mechanical heroes. But from a human-verified perspective, I'm not chasing superpowers or trying to be a comic book character. I'm simply looking to fix what was shattered and reclaim what was stolen. For those of us living with the daily reality of paralysis, the choice isn't a scary philosophical debate. We wouldn't hesitate for a second to sign up if it meant winning back our independence. One day, bionics could change my life. The collision of two worlds. In Star Trek: The Next Generation, the Borg are the ultimate cautionary tale. They are known for their terrifying efficiency, assimilating individuals by replacing their organic parts with hardware and plugging their minds into a collective hive mind. For decades, I was a neuroscientist and a medical professor teaching doctors how the motor system works. Back then, I looked at the Borg as a cool sci-fi representation of cold, mechanical perfection. Then came 2018. I was just sitting on my couch when my neck gave way. It sounded like glass shattering in my head. In that one mundane, horrific moment, my cervical spine collapsed, crushing nearly 30% of my spinal cord from my eyes to my diaphragm. The upper left quadrant of my body was paralyzed in places, and I had lost almost all function of my left arm. Suddenly, I wasn't the professor looking in, I was the patient. The motor disorders I'd spent 10 years lecturing about were now my own reality. Building the digital bridge versus joining the collective. The Borg used something called a subspace link to keep every drone connected to the group. In the real world of bionics, we are building something similar called a brain-computer interface, but with a vital difference in purpose. The Borg way. They use their link to erase the individual, turning the person into a tool for the hive. The human way. We use the BCI to restore the individual. By placing a high-resolution sensor on the motor cortex, we capture your unique neural signatures. We want the brain and the bionic gear to speak the same language, so you can move again on your own terms. When a Borg drone decides to move, then artificial intelligence decodes that command instantly. In our reality, AI acts as a personal translator. It filters out the messy biological noise caused by my injury so that when I think the word reach, A bionic exoskeleton understands that intent and finishes the physical movement my nerves started but couldn't complete. The final frontier of healing. The Borg's catchphrase is, "Resistance is futile." In the world of medical recovery, I've realized that's actually true, but not in the way the villains intended. When biology reaches its absolute limit, resisting the help of technology is futile if you want to keep moving forward. Paralysis is grueling, a daily battle with your own body. I have been an impossible miracle thanks to my family and my doctors. I regained some of my function, a feat that 98% of people with my injury never achieve. But I still feel that survivor's guilt, and with it a responsibility to push for the next chapter. Acceptance of a disability doesn't mean you stop fighting for a better future. We are moving away from the old idea of fixing what is broken and towards a future where we simply reroute our existence. Like a Borg drone, but with a human soul. We are ignoring the injury and building a bridge to the future. So if they're looking for a next 7 of 9 to test the limits of what a digital bridge can do, sign me up. This isn't the end of my story. It's just the beginning of the upgrade. The revolution has already begun. The bionic revolution isn't some far-off sci-fi dream hidden in the future. It is a reality that has been quietly and steadily unfolding for decades. While we often think of this as a modern phenomenon, the foundation was actually laid back in the 1960s with the development of the Belgrade hand in Yugoslavia. Although that early model was quite clunky and lacked the elegance of today's sleek carbon fiber gear, it was a total game changer. It provided the world with the first real proof that a mechanical device could be engineered to mimic the complex, multi-jointed movement of a human hand. Since those early days, the technology has evolved from simple mechanical tools into sophisticated wearable computers that essentially listen to your biology. Instead of just reacting to physical levers, today's bionic limbs intercept the tiny neural signals. The device then uses high-speed processors to analyze that data and translate your mental intentions into immediate physical actions. This means that simply thinking about reaching for a warm cup of coffee or deciding to take a stroll down the street becomes a seamless command that the hardware executes in real time. The real leap in this field occurred with the invention of the cochlear implant. This was a monumental milestone because it represented one of the very first times humans successfully plugged a machine directly into the nervous system. By creating a bridge to the auditory cranial nerve, the implant takes raw sound waves from the environment and converts them into sophisticated electrical pulses. The brain then receives these pulses and interprets them as clear speech or beautiful music, effectively bypassing a broken biological link. As we moved into the late 1990s and the early 2000s, this progress exploded into a new era of life-saving and life-enhancing tech, yielding the first fully functional artificial hearts and advanced robotic arms. Today we are standing on the newest frontier, the marriage of this hardware with artificial intelligence. We are no longer just building better parts. We are developing limbs that possess the intelligence to learn your specific gait, adapt to uneven terrain, and anticipate your next move. This shift is profound because it marks the transition of bionics from being a tool you merely wear to becoming a true integrated part of who you are as a human being. Bionic integration. Integrating a bionic limb is far more than a simple mechanical attachment. It is a high-stakes translation project between complex human biology and sophisticated digital code. To make a prosthetic feel like a genuine part of the body rather than just a tool, science relies on 4 fundamental pillars of integration. The structural anchor, osseointegration. The first pillar is osseointegration, which solves the problem of how a machine physically connects to a human. For years, patients had to use uncomfortable sockets that slipped over the skin, often causing sores and instability. Today, surgeons can implant a medical-grade titanium bolt directly into the remaining bone. As the body heals, the bone actually grows into the metal, creating a permanent, rock-solid bond. This allows the limb to be clicked into place, providing a superior range of motion. More importantly, it grants the user osseoperception, a phenomenon where you can actually feel vibrations traveling through your skeleton. This means that you can sense the difference between walking on gravel versus pavement through the limb itself. Rewiring the controls. Targeted muscle reinnervation. The second pillar, targeted muscle reinnervation, handles the wiring. When a person loses a limb, the nerves that once controlled it are still there, acting like live wires with nowhere to send the signals. In TMR surgery, doctors reroute these nerves into nearby healthy muscles, such as the chest or the arm. This creates a new control panel. When you think the command "close hand," your chest muscles twitch. Advanced sensors detect that specific muscle twitch and instantly tell the bionic hand to move. It's a brilliant way of using your body's existing cables to speak directly to the new hardware. The digital bridge, neural interfaces. For the highest level of precision, we use neural interfaces, which go straight to the source of the signal. This is done by wrapping tiny electrodes around peripheral nerve interfaces to catch signals as they travel through the limbs. For those dealing with spinal injuries, it can go even further by placing sensors directly on the brain's motor cortex. This is known as the brain-computer interface. By capturing your movement intent directly from the brain, the technology can bypass the damaged spinal cord entirely, catching the command before it ever hits the site of the injury. Closing the loop, sensory feedback. The final pillar is the holy grail, sensory feedback. Until recently, movement was a one-way street. You could tell the limb what to do, but it couldn't tell you what it was touching. By closing the loop, we add sensors to the bionic fingertips that send electrical pulses back to the brain. This allows the user to actually feel a real sensation if they touch something hot, sharp, or soft. This breakthrough is life-changing because it means you no longer have to constantly watch your hand to know if you're holding an object securely. You can simply feel it. It's just like a natural limb. The AI partner. This is the ultimate in AI assistance. Between your nerves and the motors sit an AI decoder. Neural signals are incredibly noisy and messy, so the AI acts as a translator, filtering out the biological static to find the specific pattern for "pick up that cup." Every person has a unique neural accent, and the AI learns yours over time. Modern bionic legs even use AI to scan the ground hundreds of times per second. If it detects a hill or a curb, it automatically adjusts the ankle's hydraulic pressure. This lowers the cognitive load, which is the mental tax of having to focus on every single step. So you can focus on your conversation instead of your mechanics. In the future, quantum chips like those being developed by Google could make this happen in real time, allowing for a level of fluid movement that standard computers just can't reach. Your bionics are learning you. In the world of modern medicine, bionic technology is no longer just a static tool you wear, it's becoming a living partnership. We're moving away from the era of dumb prosthetics towards a future where the machine actually learns who you are. Every human body is biologically distinct. The specific way you flex a muscle, the timing of your movements, and the unique electrical hum of your peripheral nerves are as individual as fingerprints. AI is the bridge that allows a piece of titanium and carbon fiber to understand that personal language. This process begins with pattern recognition, which we can think of as the learning phase. When a patient is first fitted with the bionic limb, they undergo a collaboration period where the AI acts like an observant student. As the user thinks about a specific movement, like pinching a key or pointing a finger, the AI monitors the resulting electrical signals. It isn't just looking for a simple on or off command, it is analyzing complex signatures of neural activity. Over time, the computer builds a personalized digital map of the user's intent. Eventually, the delay disappears. The moment you think about moving, the limb executes the action because it recognizes your specific neural shorthand. Beyond just following orders, these devices are now adapting to the environment in real time. Natural movement isn't just a one-way street from the brain, it's a constant conversation with the world around us. Modern bionic legs, for instance, are packed with sensors that can scan the terrain hundreds of times every second. If the AI senses a slight incline, a stray pebble, or an uneven sidewalk, it doesn't wait for the user to react. Instead, it automatically adjusts the hydraulic pressure or the motor torque in the ankle joint. This mimicry of human reflexes allows the user to walk naturally across a park or a crowded street without having to consciously micromanage every single step. By handling these thousands of tiny corrections, AI significantly reduces the cognitive load on the patient. For decades, using a prosthetic was mentally exhausting because the user had to use 100% of their focus just to keep their balance or hold an object. AI takes over these micro adjustments, which are the invisible balancing acts our bodies usually do automatically, freeing the user to focus on a conversation, a phone call, or simply enjoying the scenery. Currently, bionic technology is exploding across several key sectors. Number 1, neural interfaces, known as brain gates. These are the cutting-edge implants that connect a computer directly to the brain's motor cortex. They allow paralyzed individuals to operate computers or robotic arms purely through thought. We are even seeing bidirectional research where the limb sends signals back to the brain, allowing the user to actually feel the texture or pressure of what they are touching. Exoskeletons. These are essentially wearable robots. These electrical mechanical suits act as powered muscles that can help a patient with a spinal injury walk again or assist workers in lifting heavy objects without straining their own bodies. Number 3, advanced surgical techniques. Methods like TMR are becoming the gold standard. Surgeons actually rewire lost nerves to new muscle groups, which not only gives the patient much better control over a bionic limb, but also significantly reduces the chronic phantom limb pain that often follows an amputation. Through this combination of AI, clever surgery, and high-speed processing, we are finally reaching a point where the machine doesn't just feel like a tool, it feels like a part of the family. AI power and bionic possibilities. We are standing on the edge of a massive shift in how we think about human potential, thanks to the evolution of newer AI models and the mind-blowing possibility of switching from traditional silicon to quantum chips. Since I'm a huge fan of the Google ecosystem, and I'm actually using their tools to write this right now, they are the perfect example of where this is headed. Google's quantum technology is currently the world leader, hitting milestones that were purely science fiction just a few years ago. The real magic happens when you think about what quantum chips could do for the learning process between a person and their prosthetic. Right now, most bionic limbs require a lengthy training period where the user and the computer have to learn to understand each other. But with quantum processing, that could happen in near real time. Instead of a slow calibration, the limb could theoretically adapt instantly to the unique electrical language of your nervous system. This allows for a level of fluid, intuitive, and natural movements that standard binary processors, which only think in ones and zeros, simply can't keep up with. If you want to see the cutting edge, you can check out Google's Quantum AI Lab. However, we have to stay grounded in reality. Even with these incredible advancements, seeing a quantum-powered bionic limb at your local clinic is likely at least a decade away. While the potential for giving people's abilities that we never thought possible is very real, we are still firmly in the developmental and experimental stages. That doesn't mean the revolution isn't already happening on the ground with standard AI. Companies across the globe are making stunning progresses right now. Take Acer, a company based in Iceland. They have developed one of the most advanced bionic hands in existence, which uses sophisticated sensors to allow for gesture control. This means a user can switch between different grips or movements with just a simple, natural gesture. Similarly, the University of Utah has teamed up with German engineering giants at Autobach to create an AI-powered bionic limb. This isn't just a static peg. It's a smart device that mimics natural human gait. It gives people the freedom to climb stairs, stand up, sit down, and navigate tricky obstacles with ease, allowing them to walk much further and with less fatigue than ever before. The field is getting crowded with innovators, and if you're interested in where the future is going, there are several other notable names to keep on your radar. Companies like Medtronic, Abbott Labs, and Boston Scientific are bringing their massive medical expertise to the table. Meanwhile, startups and specialized firms like Psionic, Atom Limbs, Bionics, Cure Bionics, and Axle Bionics are pushing the boundaries of what a prosthetic can feel like. Even in the realm of direct brain-computer links, companies like Synchron, Neuralink, and Exobionics are working on ways to ensure that one day the digital bridge between the mind and the machine is completely seamless. The human verified reality. This circles back to the core idea of being human verified. As I've said before, I am not a robot, and the sheer complexity of our biology proves it. The human nervous system is so intricate that trying to simply plug a digital device into it can feel like trying to attach a garden hose to a fire hydrant. The sheer volume of information can practically blow out the device. Our nerves communicate through electrical chemical signal transduction, which is a fancy way of saying that we use a mix of electricity and chemistry to talk. Even our most advanced computers use binary, which is a simple language of ones and zeros, while the nervous system operates in a multi-dimensional way that science hasn't even fully decoded yet. For a bionic limb to work, it has to catch your thought, translate that intention into a specific digital command, execute the physical move, and then sense the environment to adjust on the fly. In a healthy body, this entire loop happens in just 1/3 of 1 second. Beyond the language barrier, we face the physical reality of biocompatibility. To put it bluntly, the human body is a hostile environment for electronics. It's warm, salty, and incredibly protective. When we implant a sensor, the immune system immediately flags it as a foreign invader. This triggers a process called glial scarring, where the body wraps the sensor in a layer of internal scar tissue. While the body is just trying to protect itself, this scar tissue acts like a thick blanket of insulation, eventually muffling the electrical signals until the sensor can no longer hear the brain's command. Then there's the issue of bandwidth and resolution. Think of a natural human hand. It is packed with thousands of sensory receptors that give you instant updates on pressure, temperature, and where your fingers are. Current bionic interfaces have very low bandwidth by comparison. We might only be able to tap a few dozen nerve fibers, whereas a natural limb uses thousands. This is why bionic movements can feel clunky or robotic. We are also struggling with proprioception, that sixth sense that allows you to know exactly where your arm is in the dark without looking at it. Recreating this closed loop feedback is one of the toughest mountains to climb in cybernetics. We also have to consider long-term stability. For this technology to truly change a life, it needs to last for decades. However, the brain and muscles are constantly making tiny micromovements. If you have a rigid electrode sitting against soft neural tissue, those tiny movements can cause the sensor to shift or even cause permanent damage. Plus, the wires or leads that connect internal sensors to the outside world are vulnerable to breaking or causing infections at the point where they exit the skin, known as transcutaneous points. From a medical perspective, we also have to consider the abandonment rate. If the gear is too heavy or the battery dies too fast, people just stop using it. Success isn't just about the surgery, it's about the mental integration. As a neurology professor, I used to tell my students, just because we move automatically doesn't mean it's easy. It just means we are really, really good at it. Finally, there is the mental mountain of neuroplasticity. Even if the hardware is perfect, the brain has to relearn how to use it. If someone has been paralyzed for years, the part of the brain that once controlled their legs might have been reassigned to other jobs. Moving forward requires intense physical and mental therapy to reclaim those old neural pathways. Despite all these challenges, the field is moving at light speed. We are seeing breakthroughs in osseointegration, where we anchor prosthetics directly into the bone, and TMR, which involves rewiring nerves to the new muscle groups. We are rapidly moving away from tools that we wear and finally entering the era of parts who we are. We are humans, and there are psychological considerations. The journey of receiving a bionic limb is often much more complex than the surgery itself. While the technology might seem superhuman, the transition is deeply, rawly human. Moving from the loss of a limb into the integration of a high-tech prosthetic involves a massive shift in how you see yourself, your body, and your mental health. From a human-verified perspective, becoming bionic is less about plugging in and more about an emotional and neurological evolution. The internal shift, identity, and embodiment. Amputation creates a fundamental rift in a person's sense of self. When a bionic limb is introduced, the brain faces a paradox. It has to turn an extra object into a part of the body. This is called embodiment. The psychological breakthrough where you stop thinking of the prosthetic as a tool, like a hammer or a shoe, and start feeling it as a true extension of yourself. Interestingly, many people find more comfort in sleek robotic designs rather than hyper-realistic ones. This is because of the uncanny valley, a feeling of revulsion that happens when something looks almost human but doesn't move perfectly. By embracing a high-tech cybernetic look, users often find it easier to accept their new identity. The cognitive reality, relearning movement. Natural movement is automatic, but using a bionic limb is a conscious effort. It requires a heavy mental tax. Every single step or grip requires intense focus, which leads to massive mental fatigue. It's easy to feel like a failure when you can't make the limb perform naturally the right way. Movies often show these as instant upgrades, but the reality is hundreds of hours of grueling physical therapy. Bridging the gap between that sci-fi hope and medical reality is a major hurdle for a patient's resilience. The neural connection, quieting the ghosts. One of the most fascinating scientific findings is how bionics can treat phantom limb pain, which affects up to 80% of amputees. This happens because of proprioceptive ghosting. Your brain keeps sending signals to a limb that isn't there, and when it gets no response, it interprets that silence as pain. High-tech bionics, especially those with sensory feedback, can close the loop. By providing the brain with visual and tactile proof that the limb is moving, the technology leverages neuroplasticity. The brain's motor cortex actually remaps itself, quieting those confused neural pathways and providing genuine relief. The social shift from pity to agency. The way the world looks at you changes once you go bionic. Many users report a shift from being viewed with pity to being viewed with curiosity or even awe. This cyborg transition can be empowering, but it also means becoming a bit of a public spectacle. However, the real psychological win is the return of agency. It's about the micro wins. Being able to hold a bag of groceries while unlocking a door, or standing up from a chair without help. These moments restore a sense of adult autonomy that disability often strips away. The human reality, survivor's guilt, and access. There is also a heavy social weight to this technology. Because these devices are incredibly expensive, a wealth gap has emerged. Those who are lucky enough to receive these miracle upgrades often feel a sense of survivor's guilt, knowing that life-changing tech is locked behind insurance battles for others. This often turns personal recovery into a mission of global accessibility. In the end, we aren't just fixing a machine. We are reintegrating a human being into their own life. The upgrade is only truly successful when you look at the carbon fiber and chrome and think, that's me. Not, that's a motor. Make me bionic. Building a digital bridge is the ultimate goal for anyone navigating the aftermath of a spine injury, which is essentially a massive communication breakdown within the body's wiring. To understand this, think of your spinal cord as a high-speed fiber optic cable carrying vital data. When that cable is crushed, your brain, which is the master controller, keeps right on firing off commands, but those electrical signals hit a dead end. The BCI isn't just a gadget. It's a sophisticated bypass system that reroutes your thoughts around the injury site, effectively ignoring the damage to restore your connection to the world. The process itself is a breathtaking marvel of modern engineering. We start by placing high-resolution sensors on the brain's motor cortex, the specific region responsible for planning and executing movement. When you think about a simple action like grasping a cup, your neurons fire in a very specific, unique electrical signature. The BCI captures this raw thought before it ever reaches the shattered glass of the injury. That signal is then transmitted to a wearable computer where AI takes over. This AI acts as a sophisticated translator. It filters out the massive amounts of biological static or background noise from your other thoughts to identify the pattern A, which is your intent to reach, while pattern B is your intent to grip. Once that intent is decoded, the system sends the command past the injury directly to the target. This can happen through functional electrical stimulation, where tiny electrodes on your skin shock your actual muscles into contracting, or by commanding a robotic exoskeleton to move your frame for you. But that holy grail of this technology, that phase called closing the loop, involves adding sensors to a bionic limb that send data back to the brain's somatosensory cortex. This restores proprioception, the essential sixth sense that we talked about that allows you to feel that your hand is closed or that your coffee is hot without having to stare at your limb to make sure it's actually working. For someone like me, this is a total turning point. In my case, because 70% of my spinal infrastructure is still intact, a BCI could act as a neural amplifier. It can take those faint, muffled signals that manage to leak through the scar tissue and boost them, using an exoskeleton to provide the mechanical nudge needed to complete a movement my muscles started, but they just couldn't finish. We are moving away from the old medical philosophy of trying to fix the problem and towards a human-verified reality of bypassing it with tech. The year 2026 has brought incredible advancement, specifically for the neck and upper body, moving far beyond the lower back suits of the past. The Cyberdyne HAL, which means hybrid assistive limb, is revolutionary because it listens to the faint bioelectrical signals that still reach your skin even after a 30% cord crush. It only moves when it detects your intent to move, which helps the brain rewire itself through interactive feedback. In clinical settings, the ExoNR is now FDA cleared for injuries as high as C7 vertebra. Its Smart Assist AI is vital for cervical patients who often have asymmetrical strength. It can provide 100% power to a weaker left side while letting a stronger right side do the work, adapting in real time as you get stronger. For home use, the ReWalk 7 now includes crutch-integrated controls and trunk-stabilizing harnesses, finally making stairs and curbs accessible for higher-level injuries. The most exciting frontier is hybrid training, where we combine these exoskeletons with epidural stimulation, which are tiny electrodes implanted directly on the spinal cord. By electrifying the cord while you walk in the suit, we lower the threshold for signals to jump the gap. This isn't just a tech trend, it's a way to bridge the gap between medical patient and bionic pilot. If I were to go down this road, my goals would have shifted towards fine-tuning my biological gains for high-tech integration through several key pillars. To achieve bionic success, I would focus on 3 practical areas: control, mobility, and identity. First is control, which is all about sharpening the brain's signals. I would practice tactile differentiation by feeling textures like sandpaper or velvet without looking, which helps prime my brain for future sensory tech. I would also work on the 1/3 second challenge to make my movements faster and more automatic. An isolated movement to move one finger at a time without the other muscles twitching. This creates a clean signal for an AI to read. Next is the exoskeleton pillar. Using a robotic suit like the ExoNR requires perfect balance, so I would use mirrors to practice symmetry awareness to keep my weight centered at about 50-50. I would also find my nudge threshold, the exact point where my own strength ends and the machine needs to take over. I would build vertical endurance by standing longer each day, which keeps my heart and bones suit ready. Finally, there is the identity pillar. This one is a mental game. I would use embodiment check-ins to visualize my digital bridge working, which actually helps my brain rewire itself. I would practice agency advocacy by tracking tasks that I do alone, proving I'm the pilot of my life, not the victim. Lastly, I would turn survivor's guilt into a mission by sharing my neuroscience knowledge to help others who are still fighting to recover. My ultimate personalized bionic milestone would be to achieve a closed loop moment, to perform a task like grasping a cup of coffee while focusing entirely on the conversation I'm having. When the mechanics of my hand become invisible and the technology becomes me, that is when the upgrade is complete. We'll see what the future holds. For now, it's physical therapy and compensatory techniques. I mean, it's worked so far. Thank you for spending this time with me today.